And basically, we decided that there's need for two conditions for equilibrium. One was the sum of the forces in any direction must equal 0. Then you're not going to accelerate in that direction. And the other is the sum of the torques, the turning effects around any axis must sum to 0. And the reason for that is if they don't sum to 0, you can spin. And let me see if I can get this pen going. So if you had, say, a log, and you pulled on one side and you pulled on the other side, and you weren't pulling in line with each other, although because you're pulling in along the same direction, you would be in, some of the forces would equal 0. So this log would not accelerate to the left or to the right. Because they're not lined up, you would spin, and that thing would accelerate faster. It would spin faster and faster and faster, kind of like you. Start moving and spin. So there'd be a rotational equilibrium. And we don't want that either. You don't want your bridge to rotate. You might not want it to accelerate, but you don't want it to rotate either. So we have these two conditions for equilibrium. The sum of the forces along a line, there's my line, and the sum of the torques about an axis, and there's my axis. So, okay. And then we say, well, just like we had before, the sum of the torques about an axis must equal 0 if it's in equilibrium. So we need to have a positive and a negative. So we'll say, let the clockwise torques be the positive and let the counterclockwise torques be the negative. And that's how we do that. So fair enough. We need to, just like before we said, well, that's going to be the positive end and that's going to be the negative end, so that they're not, we don't assume they're the same thing. So a clockwise torque would be the positive, and a counterclockwise torque, that's also clockwise, but a counterclockwise torque would be the negative. A counterclockwise torque would be the positive, and a clockwise torque would be the negative. So, 3 or 4 classic examples. We have the seesaw, we have the beam and rope, we have the ladder, and we have trusses, but you won't do trusses until you get to statics. And you go to Professor Nura, and he gives you...
My friend is taking them right now.
He gives you far more complicated things. Okay. So a seesaw is balanced. A 5 Newton weight is located at 4 meters to the left of the fulcrum, and a 15 Newton weight is located to the right of the fulcrum. Where is the weight located? So we have this. Let's just draw it out. We're going to have a fulcrum. Fulcrum is a like hinge, and 5 Newton located 4 meters to the left. So 5 newtons, 4 meters. And then we have a 15 newtons somewhere. So let's just draw 15 newtons, and we don't know what it is. So let's call it X. And then I say, is it in equilibrium? Is it accelerating along a line? No, it's not. Is it rotating faster and faster and faster, or even slower and slower and slower? Is it rotating? No, it's not. It's a seesaw. It's in balance. So it's in equilibrium. So I say the sum of the torques about a turning axis equals 0 because it's in equilibrium. But the problem is, where shall I put this turning axis? And the most obvious place is here, right on the fulcrum. It's what you're kind of taught to do. And it's a kind of lucky thing, really, because I'm going to explain to you why that's fortuitous that we picked that point. So then we say, well, the sum of the torques, so we're going to have 5 times 4, and that's going to tend to make it go in a counterclockwise direction, which is positive, added to 15 times x, and that's going to tend to make us go in a clockwise direction, which is negative, equals 0. Now, sometimes people have trouble figuring out what's clockwise and counterclockwise, and it sounds like it's obvious. But when we get to the more complicated diagrams where the force is not next to the turning axis, when the force is next to the turning axis, it's easy. But when the force is way down here and the turning axis is way up there, as drawn on your diagram, sometimes it's not so easy. And so what I say to people is, if in doubt, put your finger on the turning axis and rub your other finger along the force and see if the paper turns. And if the paper turns, does it go clockwise or counterclockwise? That's the way out of it. So watch out for that. People sometimes get these wrong because on a complicated diagram, they have trouble telling the counterclockwise from the clockwise. So we go plus 20 added to minus 15x, whoops, messed that up, is equal to 0. So 15x is equal to 20. So x is equal to 20 over 15, which equals 1.33 meters. And that makes a bit of sense. It's closer in because it's a heavier weight. That makes sense.
Could it be negative?
Well, it's going to be a negative over a negative, isn't it? That's going to be minus 15, and I took that to the other side, so that would be a negative. So, yeah, negative over negative. So I skipped that step. Shame on me. We said earlier, it doesn't matter where you put your turning axis. If the object's in equilibrium, it's in equilibrium about all axes. Just like if it's in equilibrium along a force, it doesn't matter which. If something's not accelerating in any direction, you can put some of the forces in any direction, and it should equal 0. If it's not rotating faster and faster and faster, or rotating slower and slower and slower, you should be able to put your turning axis around any point. So this should work no matter where I put my turning axis. So let's say, just for the sake of it, that I decide to put my turning axis, let's draw this diagram again. Let's say that I've not been, I'm a bit off, and I decide, I'm not going to do it that way, I'm going to do it my way. And so I say, well, my way is that I'm going to put my turning axis there. And that's quite acceptable, as long as you do the math right. And so I say, this is still x. I say the sum of the torques about my turning axis equals 0. And now the 15, or the 5 Newton, is 5 times 0, because there's no lever arm. It's going through the force. Yes?
Why is the 15 negative?
Why is the 15 negative?
Yeah, in the equation.
Because it forms a clockwise torque.
Okay.
Yeah. So it's not the 15 that's negative. It's the 15 times x that's negative. But you carry that on with one or the other of them. So you basically, where was I? So you basically say, well, the 5 is going through the turning axis. So that's going to be 5 times 0. So there's no torque, no turning effect caused by that 5 Newton one. And then the 15, well, the 15, this is not so bad. This is 15 times, well, not 4 and not x, but 4 plus x, yeah? I don't think that equals 0. I got something missing from my diagram.
The other force.
Pardon?
I'll say maybe the other force from is it
Which one?
the 5 Newton?
No, 5 times 0 is 5. We've done that. No, it's not that force. So,
You're going to hit that fulcrum.
so that fulcrum's going to have a force on it, yeah?
Yeah.
And how big will that force be?
What's that dot next
It's
to
going to be.
That's the turning axis. That's the turning axis. That's the turning axis, yeah? So what's the force upwards? Yeah, because it's in the sum of the forces vertically equals 0.
Oh,
So 5 and 15 down, you're not accelerating downwards. So there must be a force upwards to balance it, and that must be 20 newtons. Not told to you explicitly, but it's there. So we add on to that 20 times 4. But that's going to be, is that clockwise or counterclockwise? That's going to be counterclockwise. So that's a positive. Oh, bad me. This is clockwise, so that's negative. Man. So let's go through that again. The 15 times the 4 plus x causes a clockwise motion. So that's negative. And the 20 times the 4 gives you a counterclockwise motion, which is positive. And they sum to 0. So that would be 15 times 4 is minus 60. Let's do minus 60 plus 15x. We'll sort out we'll distribute that sign in a minute. Plus 80 equals 0. Let's distribute that minus sign. Minus 60 minus 15x plus 80 is equal to 0. So 15x minus 15x, if you like, is equal to minus 20. So x is equal to minus 20 over minus 15, which equals 1.33. Same answer, because it's got to be the same answer. Oh, yeah, sorry. Right. So it's the same answer. It's got to be the same answer. But got by a different methodology, different routes, but it still works. And what this illustrates is a couple of things. Number one is pick your axis wisely. Don't just pick an axis. Pick your axis wisely, because you can make the problem harder for you or easier for you by picking the axis wisely. And one of the things to think about is, if I have a force that I do not want to deal with, if I put my axis through it, it's not in my equation anymore. The force still exists, but it causes no torque. So think about where you put your axes. Yes, you got a question?
How do you know what to multiply with? How do you know what to multiply what with what?
So what is the definition of torque? What did we say torque was? Anybody? What's torque?
The lever arm.
It's R cross F, which equals R times F times the sine of the angle between. What's the sine of the angle between these guys?
Where does the sign come from?
What do you mean?
Why do you have the sign?
Basic definition of torque. If you go back and look at that diagram and recognize that we need the force times the perpendicular distance. If they're not perpendicular, you've got to take into account the sine of that angle. Just go back and study that diagram again, okay? Okay, so you've got to be careful about your turning axis. Pick a nice turning axis and it'll work out. Pick a bad turning axis and it's not that you'll necessarily get the answer wrong, but you'll have to work for it. Yes?
If both the forces are going down, is the right way always going to be negative because it's going counter?
If you put your turning axis to the left and both your forces are pointing downwards, you're not in equilibrium,
Yeah.
and you're going to have both of those are going to be positive. Both of those are going to be negative. Okay. So you've got to kind of, in your mind's eye, you've got to kind of do, that's doing that, and that's doing that. And as I say, there's nothing wrong with putting your finger on the turning axis and just rubbing your finger along that.
The reason the 15 is negative because that's the one that's going down.
No. The reason why the 15x is negative is because that gives you a clockwise torque. Okay? That's one class of problems. It's not a class of teaching, it's one class of problems. Next. Oh, by the way, in this one, a typical test question, well, not a typical test question because there's a whole variety, but look at the homeworks, because I'm not above doing a force here and an axis there and a force there and a force there, and asking you for an unknown here where it's not butting up against the fulcrum. So expect to have to be able to do some adjustment, you know. It's not just going to be this. This is just to explain it, okay? You got a question?
So the left one is going clockwise.
This guy here?
Yeah.
Or which one? On the top or bottom diagram?
That line,
Top or bottom diagram?
bottom one.
Bottom one, this guy?
So that one's going clockwise or
That one's going counterclockwise.
it's going counterclockwise?
So it's positive.
And that's because the weight's pulling it down that way, right?
No. That's because so have you got that diagram on your page?
Yeah.
So literally do this. Put your finger there, because that's the turning axis, and push. And your page is going to go like that.
I'd say, yeah, that's if you put the lever on the left.
That's because you put your turning axis there. Push with the force. Just do it now. Just put your finger on it and push. Your page goes.
Yeah, that makes sense, yeah.
And this guy, pull.
Now, what about the first?
That guy, pull. Pull. Go in whatever direction the force is and see what happens to your page. Whatever direction the force is and see what happens to your page.
But isn't the force on the left side going down?
Who cares? It's what turning effect. Does that force cause? Because I can have my turning axis here, it's still going down, but I'm going to have an opposite torque about this point. So it's the torque about the point, it's not the force's direction. So you look to your turning axis, wherever you choose to put it. I can put my turning axis there and still do this problem. I'm going to put my turning axis there, and then I pull on this, and that turns it in the clockwise direction. I put my turning axis there, and I pull on that, and it turns it in the counterclockwise direction. So it's not. So don't think about it as a force that's got a sign or a distance got a sign. It's that combination that has the sign. And the key thing is it going clockwise or counterclockwise, and that causes people a lot of grief. It sounds straightforward, but it's, you know, it's not as straightforward as we tend to think. Yeah. And the only way I can think of to try and sort this out is you put your finger on the turning axis and you move the force. Sorry, is that okay?
Yeah.
Okay, cool. Let's go to something a little bit more complicated, merely because of the diagram. This is an example where we have a piece of string that's holding up a beam. So this is a wooden beam. The red bit is a wooden beam. So you could, if you like, you could do it like that. And we know it's a 4 kilogram uniform 6 meter long. Now, torques require forces. So I'm going to immediately go from 4 kilograms to 40 newtons. And I'm going to put it in the middle of the beam because it's a uniform beam. And I suppose we've done non-uniform structures like triangles, and I suppose if I pushed it, I could give you a triangle, but I wouldn't. This is hard enough, okay? And so I have a tension in that string. Now this beam is just pushing against this wall. So, and this is what people tend to miss. There's a frictional force upwards, otherwise the beam would fall. And there's also a normal force outwards. So in these examples, part of the skill is that, frankly, I don't give you all the forces deliberately. We just don't give you the forces. So my advice is we draw ourselves our own diagram, bigger, better. This is going to be 35 degrees. This is going to be 40. We have FF, and we have FN, and we have tension. 3 unknowns by my count.
So why is frictional force going down?
If the frictional force wasn't there, which way would the piece of wood fall? Upwards or downwards? So then if it's not falling downwards, the frictional force must be supporting it upwards. Remember, frictional force points in the direction that opposes the motion or the tendency to motion. So, 4 kilogram, 6 meters long. So I know, well, this is where my diagram gets a bit hard to draw. I know that's 3 meters. And I know that's 3 meters because it's in the middle. This 40 newtons is in the middle. Let's have a look. The rope makes an angle of 35 degrees. I got that in. What is the tension in the rope? So let me change my color of my pen so that you can see different thinking at different points. Okay. So where am I? So first of all, is this object in equilibrium?
Yes.
So therefore, the sum of the forces equals 0. the sum of the torques equals 0. I can tell you now that if you try and do the sum of the forces horizontal, you're going to have some component of tension and Fn messing with you. And if you try and do it vertical, you're going to get a 40, an FF, and a T involved. So you're not going to solve it so easily. You could, potentially. But what I'd like you to do is think about solving this using torques. So let's think about it. I want to solve this in one step. I have 3 unknowns. I don't want to do 3 steps. So what trick can I use so that a force does not create a torque about my turning axis? Where do I put my turning axis? Yeah. So put your pen down on the FF direction and put your pencil down on the FN direction, because I don't want either one of those. And where do they cross? They cross there. So to solve this problem in one step, I'm going to put my turning axis there. If I want to solve it in 3 steps, I can put it anywhere. But if I want to solve this problem in one step, I put my turning axis there.
And that cancels out both forces because both of them go through the
Strictly speaking, the forces are still there, but it nullifies the torques.
nullifies.
Yeah.
That's a good word.
So then we say the sum of the torques about my turning axis equals 0. And so I look and I say, well, let's look. I have 40 newtons times 3. And that's going to be a, what is that, clockwise or counterclockwise? Clockwise. So that's going to be a negative. That's that guy taken care of. And then I need to take into account this torque, and it's going to be, oh, so I have a choice. I can either get that force times the perpendicular distance, or I get that distance times the perpendicular force. But I can't just take T and 6, because they're not at 90 degrees to each other, and torques are at 90 degrees to each other. So what I prefer to do, there's no right way to do this, but I prefer to do it this way, where I say this is T sine 35. Using my components are coming back. So I say this is T sine 35 times 6, which is the perpendicular distance. And that's going to make me go in a counterclockwise direction, which is positive. And that equals 0. Question?
Why are you using 3, not 6?
Why am I using 3, not 6? Where?
40 times 3,
Where's the force?
going down.
Well, it's going down, but where is it? Is it at the edge? Is it at the beginning or the middle? How long is the piece of wood?
6,
How far is it to the middle?
6. I mean 3.
Yeah. Okay.
So like the R is supposed to be the distance from the force.
It's a torque, so it's the force times the perpendicular distance to the lever arm. Yeah. So we're going to say this is going to be minus 120 plus 6 times T sine 35, whoops, is equal to 0. So T is equal to 120 over 6 sine 35. What does that equal? Some number. I didn't bring my calculator. This is the second day. Man, I am so out of practice. Second day I didn't bring my calculator to class. Don't believe that. So what's that going to be? 20 over sine 35, probably something like 60 or something like that. Anybody? Pardon?
11.5.
Oh, is that right? Did I mess up completely? Probably. 6 is into 120 is 20. So it's got to be more than 20, because you're dividing by sine 35, which is less than 1. So go 120 divided by 6 equals, divided by sine 35 in degrees equals.
Equals 34.9.
That sounds like it. What are the units going to be? What are the units for torque? Oh, tension. What's the unit for tension?
Yeah, 11.95.
So how are you doing? How are you doing it to get 11.95?
Isn't it-
Are you in degrees? Are you in degrees? I'll just check it. Okay. See me afterwards if you. Okay, cool. So, second level, third level, ladder climbing. Big diagram. You want a big diagram. If you've never drawn a big diagram, draw a big diagram now. Draw a nice diagram. That's a lousy diagram. Let me see if I can find myself a eraser. Yeah, let's get rid of that. Let's go back. Pen. Try and get it a decent diagram. That's 60. Says a uniform 20 kilogram. Let's immediately, it's uniform, so it goes through the middle. That's not going to be 20, that's going to be 200. 8 meter long. Let's do that as 4 meters and 4 meters. He's on the point of slipping. Okay, he wants to slip, but it's not slipping yet. The ladder makes an angle of 6 degrees with the floor. What is the force of friction between the ladder and the rough floor? So let's think about. So these are the forces that I'm inventing, if you like. So I want to put them in a different colour so we can see the you know what we're given and what we work out. So we're going to have FF, and FF is going to go in that direction. And of course there's going to be an FN down there. Any other forces in my diagram? Any other forces? Yep.
Isn't there a natural force at the top?
Normal force at the top.
Yeah.
Is there a frictional force at the top?
Wait, why is it
Yes,
point?
going up.
Is there a frictional force at the top? It says smooth wall. So, smooth wall, no.
Frictionless.
If there was a frictional force at the top, which direction would it point? Upwards. Because the tendency is for the ladder to slide down. My brother told me once he was in his factory and he was at the top trying to fix something in the ceiling. It's an open, high factory. He leant a ladder against the wall. He didn't want to stop anybody to kind of help him, so he just climbed up it. And factory floors tend to be quite smooth. They're not terrazzo, but they're kind of concrete, but they really try and make them smooth. Got right to the top, started doing something, and the ladder started slipping. And the tendency is you hold the ladder like that because you don't want to fall off it. And fortunately, this thing took a while to slide down. And it's kind of screaming to try and get help, but at some point they've got to just let him fall because he's gonna kill him, And he starts falling down. He said the only thing he could think of was to let go of the ladder. He's got to move his fingers out from what is the backside of the ladder, which becomes the bit that hits the ground. So he kind of as it went steeper, he kind of let go. It's kind of like hard letting go when you're falling. But he had to let go and still lean against it, but get his fingers out because otherwise all his weight and all that speed and all that momentum would have been right impacting on his fingers. He'd have probably broken a whole bunch of fingers. And he said it's like the longest 3 seconds of his life, it was like, from the moment he realized he was going to fall until he finally hit, he was like, man, it was terrible. Okay, so no frictional force upwards. I got 2 FNs, so this guy must be, well, it doesn't matter which we call it. We call it FN1, FN2. Let's call it FF2. It doesn't matter. Just names. I'm sorry.
Sorry, what is uniform?
What is?
What does it mean when it says it's uniform?
It's not fatter at one side than it is at the other. It's the same width, the same density. So where is the center of mass when you're uniform? It's from your middle. Okay. Yeah. So, I got how many unknowns? 3. Is this thing accelerating anywhere? No. Is it rotating anywhere? No. Like to try and solve it in one step. Put your pen on the FN1 because you don't care about FN1. Put your pencil on FN2 because you don't care about FN2. It's not the direction they point in, it's just where they cross. And they cross there.
That's the
And
rotational axis.
that's where I'm going to choose to put my rotational axis. Because by doing that, I don't need to worry about those forces. So I say, okay, let's look at this. 200. Well, let's have a look. If I'm looking at the 200, I want, let's just draw this out. If my 200 is that vertical line, my perpendicular distance is that. If my force is vertically downwards, my perpendicular distance is that. So it's going to be 200, and that perpendicular distance there is the same as that. I'm going to change the colour of pen so that this does not get confusing. So let's go to, what is it, ink colour, and let's go to a blue that you can see. So this purple will do. So that perpendicular distance there is the same as that perpendicular distance there. That distance is the same as that distance. And that distance there is going to be 4 cosine 60. Again, components come in. Agreed? So this will be times 4 cosine 60. And then I look at this whole thing and I put my finger on that turning axis and I move my finger along the 200 and I see it's going in a counterclockwise direction, which is positive. Then the only other force I need to deal with is the FF, call it FF2 in this case. And that FF2 goes off along this bottom line here, so the perpendicular distance I want is that. And that perpendicular distance there is the same as that perpendicular distance. Oh, that distance is the same as that distance. And that there is 8 sine 60. Again, trig comes in. And I put my finger on my turning axis and my finger on my FF2 and I move it and I see it goes in a clockwise direction, so that's going to be a negative. Equals 0. So this would be 800 cosine 60 is equal to, let's just take this to the other side, 8 sine 60, just let me finish, 8 sine 60 times FF2. So what was your question?
Why are you multiplying 200 by 4 cosine 60?
So, what is a torque?
Force times lever,
Okay, so what is my force here?
200.
So 4 cosine 60 is my lever arm.
Why is that your lever arm?
So it's got to be the perpendicular distance. So you go to your turning axis and you go to the axis that has your force on it, and you say, what's that perpendicular distance? And figure that by components, yeah? So, I have FF2 is equal to 800 cosine 60 over 8 sine 60. FF2 is equal to 100 over tan 60. It turns out it doesn't matter. Just work out what that number is. 100 cosine 60 over sine 60. What does that work out to be? 57.7? Sounds about right. So what do you think?
I have no clue what you just did.
So you got to have a good diagram. If you don't have a good diagram, you're kind of lost. And you got to pick a good axis. If you pick a poor axis, you're going to do a lot more work. This is solving it in one step. Can you imagine trying to solve it in 3 steps? The good thing is that we tend to use the same situations. I'm not going to give you some wacky thing. I'm going to give you a ladder, or I'm going to give you a beam been pulled, or I'm going to give you a teeter-totter, or maybe 2 of them. It's not going to be something you've never seen before. I could ask you for different things, like I could ask you for FN1 in this case, rather than FF2. I could ask you for FN2. I could ask you for the coefficient of friction, in which case you'd want FF2 and FN2. So, and they're in the homeworks, and there's worked examples on the, not on the classroom bit, but on the if you look at the videos, there's examples there. Just for the sake of it, if I asked you to find me FN2, let's do it. FN1, if I asked you to find me FN1, where would you put the turning axis? You do bottom right, you do down here, because you want to get rid of that FN2 and you want to get rid of that FF2. So bottom right would be good for that. If I asked you for FN1, that's not, so if I asked you for FN2, that's not so easy, because FN1, which you don't want, and FF2, which you don't want, are perpendicular. So you couldn't do that in one step. What you'd do is you'd say, well, that equals that, and then you could put the same symbol in for those. So you could do it in one step, but it wouldn't be so straightforward. So look at the homeworks, and then just go through them. There's going to be some kind of torque question, static equilibrium question on your test. It's going to be there. We've got to draw a bit of a line now, and we're going to do something that's just a little bit different. It's material science. My first job in the States was material science and engineering, and I didn't know much about it. I did materials physics, but by happenstance. I did semiconductors, and it happened to include materials physics. When I first came to the States and saw the department, I was really unimpressed, because they were casting bits of aluminum and making pots, and it looked a bit like a craft department rather than a science department. And even though on the 3rd floor they had all the semiconductor stuff, it was really old. It was like very interesting. In Britain, departments buy equipment and they share it. In the States, each faculty member is kind of like on their own. And so they tend to scrounge around for equipment a lot more in the States for an individual. So my boss had old equipment, and he was like, man, he's got old equipment. I've never seen equipment as old as this. And, you know, he's still doing good work, but it was old equipment. So it was a bit shocking. So I was not too impressed. And then I started attending a few seminars, and I was a lot more impressed. So I was thinking, man, you know, somebody's doing something somewhere. And then I had to teach a class, just this one class. And I was a bit surprised that the students were like smart. They were like, you know, they weren't making pots all the time. They were actually doing math. And it was significant. And then I started sitting in on more classes, and and then they started asking me questions, and they realized I didn't know any material science. So they started being condescending and polite to me, whereas I'd been condescending and polite to them, kind of thing. You know, it was a real reversal. And what I realized is that those people, they didn't know quite as much physics as I did, but they knew a lot more material science than I did. And for getting a job, that was really valuable. For research, you know, my research experience was like their research experience, but what I didn't have was that underpinning. So those courses that said material selection, and I remember kind of laughing and going, oh yeah, like they teach to open the catalog, you know. It's like, I mean, what do you need to know? It's like you want a valve, you look up valves, you know. That was my naivety. Their material selection was which alloy of aluminum shall we use to optimize our performance in this brewing vessel. I knew nothing about, I wouldn't know where to look in my catalog for that. So they were really quite sophisticated in their knowledge. When they came out as an undergraduate, they were worth a lot more than when I came out as an undergraduate, because they knew a lot more. And I'm not trying to talk you into it. I just want you to be aware that there are these areas of engineering that you might not have heard about in school that are really quite interesting. So you don't have to do physics or mechanical or electrical or civil. There's these other choices out there that you might find right up your street. And just to understand that there's a lot of knowledge in each one of those disciplines. So there's a lot of skills. So this is kind of reminiscent for me, because this has a lot to do with the material science, although I must confess it's like the most boring bit of the material science, that you're getting a taste of it by one of the boring bits. But anyway. So we're going to talk about materials properties, and as a physicist I think in terms of atoms, and that's it. And that's not good enough. So what we want to know is, I'm building a suspension bridge. What do I make the wires out of? Copper? Steel? Which type of steel? Spaghetti? You know, which ones do I make them out of? They're all the right shape, but which is the right stuff? And that's the engineer comes in. And they have figures of merit. They have books filled with figures of merit that say, this is for that alloy, and this is for that alloy, and this is for that alloy. You can find, for example, something we've done, coefficient of friction, you can find it if you look hard enough for every combination of wood available. If you want wood sliding over wood, well, oak over elm, you know, it's there. You can find it. Some obscure thing over some obscure thing, you can find it. Same goes for this. We want to know something about deformation of materials. This is the choice. This is the region they've chosen to pick. So deformation of materials. And there's basically a linear version of it, which is basically stretching a piece of wire, for example, or a metal rod or something. And then there's an area version of it, which is like getting a textbook and moving the front face forwards and the back face backwards and watching it kind of tilt. And then there's a volume version of it, which is putting it into a bathtub and kind of increasing the pressure of water and seeing how much it compresses. And you need to know those things, because if you're making something that's going to be stretched, you want to know how much it stretches. And will it stretch the same as this other material? And if you're going to shear something, you're going to pull and push, then you've got to know how much it will deform. And you can't go from first principles. As a physicist, I'd like to say, well, you just work out the interatomic spacing, and you take into account, you know, van der Waals forces, and you do this, and you come up with this equation, and there's your answer. It don't work. It's too complicated. So the pragmatic approach is measure it. Just measure it. And then put it in a book so we all can share that value. So the measured value is called Young's modulus, shear modulus, and bulk modulus.
Equations from
Okay? Well, and then the modulus is the stress over the strain. And the stress is like the force per unit area. And the strain, in this case, is the extension over the original length. And that kind of makes sense. You got more force, narrower wire, I expect more stretching, less force, bigger cross-sectional area where I expect less stretching. There's more atoms to keep it in place. So it kind of makes sense. And this next one, this is actually, I did this wrong, that's a delta. And so in this next one, well, we have the stress, which is the force per unit area. Now the force is on the top and the bottom surface. This, of course, the force was here, and there's also the support force there. So this is the F, and that's the F. In this case, the area is not the cross-sectional area. It's the flat area, because those planes are moving next to each other. It's like they're moving across each other, like a whole bunch of plywood. Each piece of plywood slides over the plywood underneath it. So it's that area, it's, if you like, it's that area I'm interested in. And delta x is how much you can deform this thing, and your original length is not the length of the sheet, but the perpendicular length. So it's the same looking equation, but the interpretation of the diagram is different. And then the last one is the stress over the strain force per unit area divided by, well, my volume is decreased. So it's my change in volume, which would be it's going to be a negative. It's got a number, give it a negative sign and put it over the original volume. Frankly, I don't care about that one. I want you to know it's there. These two, fair game. Okay. If I take my wire and I stretch it, I find that if I just stretch it a little bit, it gets longer. If I take all the weight off, it goes back. If I stretch it a bit more, it gets longer. If I take the weight off, it goes back. If I stretch it more, it gets longer. If I take the weight off, it goes back. If I stretch it more, it goes longer. I take off the weight, it goes back. And if I double the stress, I double the strain. If I double the force per unit area, I get double the extension divided by the original length. Nice, well-behaved wire. At this point here, the proportionality limit, kind of weird things happen. I start getting more extension for a given load. It should be following this linear path, but I'm getting more extension. But if I take the load off, it goes back. What's going on there? This is my take on what's going on there. You have 3 atoms and 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 3 atoms. And as you put more load on, the top 3 and the bottom 3 get stretched out because these are all slightly different positions, yeah? You're not changing the material. You're kind of just stretching it out. And at some point, and that's nice and linear, and then at some point you start getting a bit of non-linearity creeps in. Okay. But it will go back. It's all electrostatics. Then you get to that point there, which is the elastic limit. And what happens there is this starts, oh, I'm going to go to 2. And you know what? I'm going to go to 2. And you know what? I'm going to go to 2. Now I've got an extra row of atoms in here. And now I'm going to go to 3, say. And now I'm going to go to 3, and now I go to 3. And when you go back, you've got not 1, 2, 3, 4, 5, 6 rows of atoms. I've got 1, 2, 3, 4, 5, 6, 7 rows of atoms. That's never going to go back to the same length because I have 7 rows of atoms rather than 6 rows of atoms. That's why beyond this point it does not come back. That's my take on it. Material scientists probably like shaking their head and going, man, 5 years and it didn't even get that right. But you know, there's some wonderful tricks. There's this classic thing where you take a piece of single crystal copper and you give it to somebody like me, and you say, can you bend that? And I go, oh yeah. And then you give it to the biggest person in the class. And you say, oh, do you mind straightening that out for me? And they cannot straighten it out. And it's like the material's no longer the same. Me bending it changed the material in such a way that although it's still pure copper, it's no longer single crystal copper. It is full of defects, structural defects, which pin the structure and mean you cannot change it. So pure materials are actually, so single crystal materials are actually, in many cases for structural things, the last thing you want. And the material science department has all these stories about people. Guy comes into, this guy, Ambrose, Professor Ambrose's office. He says, a student comes in to see me, he's got a bicycle in 2 bits. He says, this bike is like, I don't know, so many $1,000, and I was riding it to school and it just broke in 2. Picks it up, it's a very light bike, it's titanium, one of these titanium alloy frames. Says, this is crazy. Can I take it? Yeah, sure you can. I've got medical bills, I want to sue these people. So he takes it and he does an analysis on the structure, and he finds out that it's not what it's supposed to be. It's got these huge grains in the material. Should be very small grain, very strong. Got these huge grains in the material. So this is the wrong kind of material. They used it. And then he looks and he says, hold on, isn't your name Simpson? And the guy goes, yeah. And he says, the bike's called Simpson? Oh, well, he said, this is like the bike of my life. So I decided I was going to get a paint job done on it. So he bought the bike and he took it to a paint shop and they sprayed it and they put his name on it. And then, well, what do when they spray things? They bake the finish on. So they took this paint, and to make it nice and robust, they put it in a furnace and they cured the paint, if you like. Yeah? Pardon? I think that's, yeah, they did, yeah, okay. And that process, that annealing, changed the structure of the bike he bought. He bought this really expensive alloy, and he changed it into a different alloy that wasn't strong. And so the reason why his bike broke was because he had done that. And they have all these stories of it, just fascinating stuff. But this is not the most interesting bit of it. And here's a typical example. A 60-kilogram block hangs. This is 600 newtons. From a wire of cross-sectional area, that's going to be 2 square millimeters. The wire was originally 4 meters long, but extends by 3 centimeters under the load. What is the Young's modulus? Young's modulus equals stress over strain, which equals the force per unit area over the extension over the original length, which if we rearrange it is the force over that area. That, I think I'm right. Yep. So y is equal to the force, which is 600, times the original length is 4 over my extension, which is 3 times 10 to the minus 2 meters, because it's centimeters, times my area. And my area is equal to 2 times 10 to the minus 6 meters squared. Question?
What's that stem over?
Stress.
Oh.
Yeah. Okay. So this is going to be 24 over 6 times 10 to the minus, what's it going to be? 6 times 10 to the minus 8, which equals 400 times 10 to the 8. And what would the units be? Okay, this is going to be newtons, meters over meters, meters squared is newtons per meter squared. And what's a common, well, you haven't done it yet, so I'll tell you. The common unit for newtons per meter squared is also, it's the Pascal, it's pressure. Yeah, either one's acceptable. You know.
Is it to the negative 8 or is it constant?
Minus on the bottom becomes plus on top.